Okay, so in this particular lecture, we are going to look at some more examples of the one-dimensional maps. So we'll be looking at the tent map, and very closely related dynamical system, the Bernoulli shift. Or the map on a circle. So tent map is an example of a piecewise linear map. So what do we mean by that? The tent map is given by the following equation. So this simplifies to or I'll just write down the thing as 2xn for xn less than half and 1 minus xn for value of xn greater than half. So xn plus 1. This is how the map looks like. So I have 1 comma 0 over here. This is 1, and the map attains its maxima at the value of half. So x is confined between 0 and 1. And under these conditions, this particular map, the orbit remains bounded between 0 and 1. So any condition starting from somewhere between 0 and 1 remains there only. So the orbit hovers around 0 and 1, doesn't exceed it. So this map, the tent map, is a very, I should say, elegant example of, in general, complexity. So it's a very simple map, a piecewise linear map shaped like a tent, which is responsible, or which can be used as a paradigm to explain some very rich phenomena in nonlinear dynamics. So geometrically, what's happening in the tent map? If you look at it, we'll again draw this. This is half, this is 1. So this map, which I'll again just import the definition from here. This can be visualized as an alternative sequence of stretching and folding. So what happens is that you start with an interval 0, let's say half, 1, and you stretch it. You stretch it to twice the length. So this point gets stretched over here. uh, Over here, and similarly this guy gets stretched to 1 over here. So we stretch it in the first step, and then this gets folded back. So this is the folding step, such that this point gets folded back to 0. This guy. So this, you can see this like as a chapati flour or a dough. You're making a chapati, you're stretching it, folding it back, stretching it, folding it back. But this is essentially what's happened, and this alternative stretching and folding is captured by this equation over here. So intuitively it's clear the origin of chaos in such systems. So this is this stretching and folding at each iterate gives an exponential divergence for nearby points. And of course, the process of folding also keeps the orbits bounded. Something between 0 and 1 gets mapped back into 0 and 1 because of this folding process. And not only that, folding also makes the map invertible. Sorry, non-invertible. I beg your pardon. Non-invertible. And what do I mean by non-invertible? That means that I have 2 points on the map. Let's say these guys. These 2 points, x0, x0 prime, they get mapped back to the same future point. So this is x1. So in general, this is xn plus 1, and this was my xn. So these 2 points get mapped to the same point, and that's, we break this one-to-one correspondence, and our map is essentially non-invertible map. Yeah, so this map becomes non-invertible, and we have a map which is piecewise linear, which is non-invertible, which undergoes stretching and folding also, and that essentially is a very simple example of non-linear dynamics or unpredictability, exponential sensitivity to nearby conditions arising in a very simple system. So now we can also look at the map iterated m times. So that's the symbol of the map iterated m times. How would that map look like? So I have the iterate after m time steps given by the application of the map to an initial condition xn. So I have an xn, I iterate the map m times, I'll get this guy, which means basically the map is applied m times. So let's take, how does it look graphically? So let's take the example of m equals to 2. So which means essentially xn plus 2 is equals to the map applied twice. And graphically, what does it look like? So on the y-axis I have got xn plus 2. What will happen to the fate of the map after 2 time steps, and this is xn. And the map, as we also saw in the case of the logistic map, becomes more complex with 2 bumps instead of 1 occurring at, let's say, can you guess this point? Which point on the map after 2 iterations is going to yield 1? Well, it's going to be 1 by 4. And symmetrically we have 3 by 4, this is half, and this is 1. So this is the map m square x. So let's see the pattern emerging. So we see a pattern emerging. So we have our usual map, this guy, and we have mx. The second iterate of the map, or the map m's of x, or m2x which takes any point xn to the second time step, that look like, I'm not drawing them to scale, but you get the idea. So this was 1 by 4, this was half, this was 3 by 4, this was 1. Over here. And we can repeat this pattern m times, which essentially would give us, well, so the ordinary map mx, or which I would call m1x, had one bump, m2x had two bumps. A map applied m times well, it's going to have so on and so forth. It's going to have so this pattern repeats. Ultimately, this is 1, and this is going to have m of these bumps, and the first maxima would occur at 2 to the power of minus m, the way it was occurring at 1 by 4, 2 to the power of minus m. So this is essentially what's happening to a map that takes xn to forward by m time steps. And of course this is 1 because the map always remains bounded. So you also notice that notice the behavior of let's say this particular point. This particular point on the map goes somewhere here, and a point here that is lifted very far off. So this point on the mth iterate, let's say this point, this particular point is going to be very close to 0, whereas a point over here goes after the mth iterate of the original map somewhere here. So roughly an error in specifying the initial condition. So this error was roughly of the order of 2 to the power of minus m. An error in initial conditions of the order of 2 to the power of minus m results in the mth iteration xn plus m of the original map iteration going anywhere in 0, 1. And this is actually the consequence of what we're talking about, exponential sensitivity. 2 points very close to each other, separated by some error of 2 to the power of minus m, after m iterates can be anywhere on the map. M iterations, the map. So this is actually, in some sense, you can say also the source of unpredictability that your small errors amplify. So this was an example of a tent map, such a simple map, and it was giving rise to beautiful phenomena like unpredictability, exponential sensitivity, and in general a very rich dynamics arising out of a very simple system. So with that example, let's see our second example for today, the map on a circle. Or we also call it the Bernoulli shift. Why we call it the Bernoulli shift? We are going to come to it soon. So we have this is the map, and it's a very interesting modulo means. So modulo means this is the equation of the map. Basically remainder arithmetic. So what does modulo mean? This map do? You, in the first iteration, you again stretch the map. Or you stretch the initial condition. Xn value multiplied by 2. Second is you consider the remainder after division by 1. Division by 1. So in a sense you have this guy 1. So you have half, you have 1, xn, xn plus 1. This is how this particular map looks like. You stretch the map by twice, and then you divide by 1 whatever is the remainder. You work with that, and those are the subsequent iterations. So you can see this looks very similar to the tent map, just the shape is a bit different. How would the mth iterate of this map look like? Well, as usual, you'll have m bumps. So I have this guy as xn plus m, xn, and I have this guy as 1, and these guys occur at 2 to the power of minus m, 2 into 2 to the power of minus m, so on and so forth. So why is this map called as the map on a circle? So this is the mth iteration of the map on a circle. Well, you can regard the modulo arithmetic as you can consider x to be an angle, and mod 1 is essentially completing the whole motion on a circle. So essentially you start with a circle and you have the angle x and you stretch it. to make the circumference twice. So this is B, this is the stretching, sorry, A, this is the stretching. Then what happens? Then you essentially let's go it on the next page. You twist the map into an 8 shape. So I'll just mark one point to let you know what's essentially happening. So this is the twist operation. This is the B part. And then you fold it back again. This points remain this. And this is the C fold. So this operation of stretching the map to twice the size, twisting it in the shape of an 8, and then folding the top half onto the bottom half again, this essentially is what's happening through this operation. And that captures the essentially what's happening schematically, stretching, twisting, and folding back again. That's what's happening to the map. And well, you can notice all the stretching and folding back leads to a chaotic separation of nearby points is apparent. And when we call that this map is also known as the Bernoulli shift, what do we mean? So this map can also be viewed as starting from the decimal representation of a point in binary. So I have A1, A2, A3, A4. That's how I am representing a point between 0 and 1. This guy. So here each of the digits is either 0 or 1. So what really happens? What does the map do to this sort of a thing? So essentially this map boils down to, well, you start with a condition A1, A2, A3, A4, A5, AN. The first iterate essentially shifts. So you get the second iterate will give you another shift. Now AN becomes here AN plus M, I don't know what. So multiply by, so what's essentially happening? So this is exactly what's happening is that you lose one digit and the entire decimal sequence or the binary sequence of 0 ones just shifts towards the left. So essentially a multiplication by 2, you can look at it up. You can think about it. Multiplication by 2 shifts the entire map. So in a sense, your this would become A1 dot, A2, A3, A4, A5, so on and so forth. That's your multiplication by 2. And then the mod operation, mod 1, and just taking into the remainder into account, will throw off this thing, and you are left with this guy. So this is what is known as a Bernoulli shift, this entire sequence of process. And that's why the map on the circle is called the Bernoulli shift map. And you can notice that what's happening in this particular map. So let me just copy this again. Eventually, once you reach, let's say at xn minus 1, that would be something like an plus 1, this thing. So a small change in initial conditions, that is a change in digit towards here, eventually you will shift it and this is going to become very significant. So a small change in initial conditions, and that's essentially what chaos is. Very small changes in initial conditions leads to exponential sensitivity. A small change in initial conditions, that is a change in digits towards far right of the decimal, becomes significant eventually. So I have two conditions. They differ from each other very so slightly. Well, eventually those errors are going to become significant after many iterations. So that's why this is a example of chaos. The system remains bounded, yet it is very sensitive to small changes in initial conditions, and the small errors really indeed amplify. Thank you.